Hello, everyone, and welcome. Welcome to TigerBeetle, a show where we take this database called TigerBeetle and try to understand how it works. And because this database is written in rather idiosyncratic style, using a very low language, Zig, using no dependencies except the operating system API, and I mean, even for the operating system API, we actually use only the most simple system calls. Because of this inherent simplicity, this database is useful not only to understand how to write this particular database, but also could teach you bigger themes, bigger topics in distributed systems and databases. Basically, it is an extremely nice case study. And today we are going to start a new topic because previously, I think it took us about 5 episodes. We discussed how we do upgrades at TigerBeetle. We finished with upgrades. And last week, if you recall, I promised that this week we will start looking into queries. And well, as usual, I'm always telling you lies. We aren't going to do queries today. Instead, today we will look at the adaptive routing. Why is that? Because that's actually a relatively recent addition to TigerBeetle, and I realized that while we did implement the adaptive routing, I don't think I've actually explained it on TigerBeetle, and this could be interesting. I mean, we could just go and do this. Okay, so let's start with a picture. And I don't want Russian layout. Okay, so what is replication and how it works at TigerBeetle? So if you recall, TigerBeetle is a distributed system which runs 6 replicas in a typical setup. And well, why 6? Please watch one of the previous episodes of TigerBeetle where we were explaining consensus and where we were explaining flexible quorums, which allow us to run an even number of replicas in the cluster. Okay, so one of those replicas is going to be a primary. And the job of a primary is to take a request which is originated on the client So this is a request which goes into the primary and comes out of a primary as a prepare. And the main thing which this prepare has is it has a certain op number assigned. So I don't know, like op number 92. So the job of a primary is to order requests relative to each other, to decide which request happens first and which request happens second, etc. So now, once we have this prepare, we really want to broadcast it to every single replica out there. Because, well, we are a distributed system, we want to replicate our data such that even if some part of our cluster is unreachable, together we still have enough availability, enough durability to preserve our data. So that is what we want to achieve. Okay, so how can we do this? And the most kind of like naive, straightforward, I can't understand why this is so laggy. So the most naive and straightforward approach here is to just broadcast this message from a primary. So once a primary converts a request into a prepare, it goes and broadcasts this request to anyone else. But this is really a pretty poor approach. And the problem here is that this requires that the primary has higher bandwidth than every other replica. So you see, we have kind of like 1x input, but we have 5x output, which is really not great. And for other replicas, will also have like this 1x bandwidth. So that means that because every replica can be a primary, and we need to provision our network to allow the primary to do its job, majority of the links would actually be underutilized. Will be utilizing only 1/6 of available bandwidth on every replica which is not primary. And this is kind of like not great. This means that we aren't using cluster resources efficiently. So we aren't going to do star replication. We don't want to incur extra bandwidth costs. Okay, so how can we optimize this? And how TigerBeetle worked until just a couple of months ago? Well, if you think about this carefully, you might want to do something like this. You might want to do a ring-shaped replication where I'm very bad at drawing arrows. Where the primary sends a prepare to the first backup, and the first backup sends to the second backup, the second to the third, third to the fourth, fourth to the fifth, and actually the last one shouldn't be sending these anywhere at all because like this thing starts with the primary. This is much better. This achieves bandwidth balance across all the replicas. Primary isn't using any more network than other other replicas in the cluster. And this is actually what we originally implemented in TigerBeetle, and this was working great for us for about 2 years, I think. But still, there is this very unfortunate, very poor issue with this approach. And that is, it deals poorly with message loss. So let's say that we are running this on a network which is not 100% reliable. Let's say we are running this on a network which drops certain fraction of messages, like, maybe every 10th message or something. And let's say that this message got dropped. So okay, this is embarrassingly slow. Like we don't have this message. Can we do something here? Okay, why is this so like incredibly slow? Can I just clear my canvas or something, because it is positively impossible. Can I just just say like, hey, could I please do everything again? Well, okay, whatever. We'll bear with slowness. Safari is like horribly slow recently. Like GitHub is slow, and like this thing is also slow. But I love Safari. Well, anyway, what happens if we drop a single message here? Well, you see, we need to propagate message to at least 3 replicas for it to be considered committed. And because here we propagated only to 2 replicas, well, like, message isn't going to get committed. And that means that we need to wait our entire prepare timeout and then submit it again against a different replica. So if we go and look at our code, finally, you see I've added this adaptive routing, which is today. Okay. So we have this like on prepare timeout thing where we say, okay, if we are waiting for a replica to process our prepare and respond to us with acknowledgement with prepare okay, we are going to send to like round robin across the replicas we haven't heard from. And I mean, that is fine. That gets eventually, so like okay, let me try to do this however painful it is. Okay, so let's say like this message crashed, but then we retry, and let's say we send it to this replica, and then it replied to this replica, so we got our 3 out of 6 replication quorum, and we commit stuff. But then, well, like see, like these 2 replicas do not get the message, so they will have to invoke repair protocol, but kind of like we sort of still like get out of dig ourselves out of the hole. We still managed to commit this message, but 2 problems here. One is that we do have to wait for a timeout. So if your network isn't perfectly reliable, periodically you are going to see tail latencies. And the second question is that we incur by modality. So imagine that you are operating at capacity. Your network is like saturated, but everything is okay. So your network is saturated, but you process every single message. Everything is fine. You are like serving the load. And now, what happens if the network becomes slightly buggy? What if we drop every 10th message or something like that? Well, first of all, because actually this replication involves more than a single message, the probability that a replication doesn't work is quite high. And remember, it's not only that we have prepares going through the screen, also every replica responds back with prepare OK. And replication only works from perspective of the primary if both a prepare and prepare OK were delivered. If we lose every one, if we lose at least one of those messages, we get retransmit. So this amplifies probability of failure. So okay, that means that with the message loss, actually we aren't going to be able to process every message without retries. So for some significant fraction of messages, which is larger than the fraction of network packets dropped, we are going to incur this retransmit penalty. But now remember that originally we operated at capacity. And now when our conditions become just slightly worse, we suddenly start to do a retries. So that means we increase our load. And now we are operating over capacity. And actually, the amount of message dropped might increase because of our retries, because we are now pushing our network beyond its capacity. So we might have a meta stability issue here. That is, it might be the case that we have two stable equilibria. One is where we are sending many messages and none of the messages are dropped. And a second point where we send a lot of messages and some of those messages are dropped and we are retrying, and that's why we are sending a lot of messages. And kind of like, you still get the stuck. So again, the load to the cluster, the incoming volume of requests is the same. But the way the cluster behaves processing this request might be bimodal. In the first mode, we process everything without any failures, and that is fine. But then, randomly, maybe there is some cosmic radiation or pigeons chewing on IP datagrams or whatever. Just a single message gets lost. And then we send a retry, increasing the load on the network, which kind of causes the network to drop more messages, which causes us to increase more load. And then we earned this second stable equilibrium where, despite the network being the same and despite the original load being the same, we aren't capable of processing it because we increase the load artificially via retries, which in turn increase the probability of messages being dropped, which in turn requires us to do more retries. So this is bad. Let's take a step back here. What is the fundamental problem here? The fundamental problem here is this logic of retrying after timeout in case of failure. This really is a systems killer. Because if your reaction to failure is to retry, that means that failure increases the load. And increased load naturally increases the probability of failure. So you want to avoid reacting to failures. A reliable system doesn't change its behavior in the case of failures. The reliable system behaves the same regardless of failures, and just kind of like sort of steamrolls over this whole issue. And a good example here, like how you want to solve the systematic issues, is like erasure code and redundancy and sorting. So imagine, okay, forget about TigerBeetle. Let's say that we are building something similar, something much simpler without any kind of consistency guarantees, like, just store of data. Our API is that, like, given the key, we want to retrieve the data. And for redundancy, we actually store data on multiple different data centers. So what is, let's say, I don't know, let's say we store like 3 copies of data. What is kind of like a naive way to code the system? So you get a request, hey, I want data for this key. You look at the key and you determine which 3 data centers this data is on. Then you select the data center which is closest to you, and you go and request data from this center. And when it arrives, you forward data to the user. If the data doesn't arrive within a timeout, well, you flip a coin and pick one of the remaining 2 data centers. And you actually, I think, let me maybe draw this as well. You go and you send it to the data center. So let's say we have data center 1. Let's call it A. Hey, it is no longer slow. I wonder why is that. B and C. And well, I just slow again. And then we have like front end, and then it goes like here, and then here is a failure, and then after timeout we go here. Well, this is kind of like the same bad by modality, because if our data center A is available, we do only single request to the data center per user request. But as soon as this connection goes down, we suddenly start to do twice as many requests. And this actually might bring down the data center B and data center C because we increase the load. So this is not how you want this data. Instead, what we actually do is that we want to use XOR encoding here. So let's say that this is our data. The way you want to store this data is not by blindly triplicating this data across data centers. Actually, you want to cut this by 2 halves, and let's say this is like left, and this is right. Let's say that right is green. Okay, and you want to send left to data center A, you want to send right to data center B, and you want to send left XOR right to data center C. Okay, I don't want. It doesn't really matter, but I mean, I've picked the colors, so I gotta use colors. Okay, so you send left XOR right to data center C. And when a request comes into your front end, what you are actually going to do is that you are going to request half of the data from 3 data centers instead of requesting like full copy of data from one data center. And you see that this actually just not 3 times as much data. This is just um, 1.5 bandwidth because you're sending half of the data over each connection. So instead of like receiving 2 halves, you receive 3 halves. But then it doesn't matter that no, it doesn't matter. You only need, despite sending only 3 requests, you only need 2 responses to reconstruct the data. So if we get a response from A and B, we directly can reconstruct the data by concatenating left and right. But if we only got responses from B and C, then we can reconstruct the left by XORing what we got from C with what we got from B. And then we get our left to right, and we can again concatenate this. So in this system, we send 3 requests all the time, but one of them is redundant, and we don't even notice if a failure happens. We only wait for 2 fastest requests. So we simultaneously reduce latency versus like tail latency tolerance. And this is also ability to deal with a failure without introducing bimodality, without increasing the load on your overall system. And this is like really powerful. And actually, let's repeat that idea that we are killing 2 birds with the same stone. We are tail latency tolerant, so we are as fast as the 2 fastest of the servers. And we are tolerant to the failure. And this is actually the same idea, because there is no such thing as binary failure. Failure is a continuum. There is no distinction between the system completely failing and the system being very slow. Like failing system is indistinguishable from completely crashed system if slow system is indistinguishable from crashed system if the slow system is slow enough. And similarly, crashed system will at some point will return and it will answer your request. So the right thing, the right frame of mind to think about these problems is to think only about fail slow case. Like, how do you detect if something is slow? How do you recover from that? And well, you want to use this tail latency tolerance tricks where you send several requests and you don't want for the laggards. You don't wait for the slowest ones. Okay, so going back to our replication where we don't do XOR trick, how can we apply the same lessons here? We could condense this to this rule of thumb. If you are sending a single message, you've already lost. Because a single message can always get dropped on the floor, and that means that you have to retry it, because there's no other way for system to just route around this single dropped message. And this is the fatal flaw in our ring topology, because in a ring, if you cut any single link, the whole thing just unravels. So ring replication, while it is very good for balancing bandwidth, it is very bad for failure tolerance, because it forces you to do a retries. So that means that we have 2 systems. We have a system where we do star replication, and that is bad because it increases bandwidth asymmetry. And we have a ring replication, which is very symmetric, but is prone to failures because every single message which is sent over the ring is critical. So how can we fix it? What would be a better system to route messages from? Before answering this question, let me also ponder. Let us also ponder another case. So, okay, let's think back about our ring system for now. And let's say that this time everything's actually all right with network messages themselves. So the network is fine. Like, we send this ring. But this time what happens is that we have a node crashed. So this node here is dead. Okay, so this kind of like doesn't really matter for a single message. Because, okay, yeah, this node is dead, so we don't have this arrow and we don't have that arrow. But at some later point, this node realizes that, hey, I want to retry, and like it will send a message here and it will be fine for this message. But then for the next message, it will also send to this node using this ring, and then again, it will fail to send to the node which is crashed. So for the next message, we'll also need to do a retry. So another problem with ring replication is that it kind of like assumes that topology of the network is fixed. That it cannot, it really behaves stupidly when there is like entire node failure. Because what we actually want is what we like just want to dynamically change the route. If we learn that a node is dead, we kind of like really want just to change our replication topology to jump over this failure node. Like we want to dynamically change the ring topology. Okay, so that is another ring failure. Here is another one. Let's again remember that failure is never binary. That failure is a question of degree of slowness. And let's say that we started with like this super nice working and perfect network, but then something happened. Then for some reason, like a switch on path between these two nodes bugged out. And it didn't completely fail, but it kind of like, got a little bit wobbly. That you kind of like still can send this message, but it's like, really, really slow on this link. It's not like it doesn't completely work. Maybe we even are hitting our deadlines before the timeouts, but we're still like, plus 100 milliseconds latency, which is like not great. So again, this is also the case where we want to change our topology dynamically. And maybe actually, like if we measured all the latencies and try to figure out, hey, what is the fastest way to replicate in this situation, maybe what we'll get is something like this. So maybe you actually want like send here, and then this link is actually fast, but then this want to send here, and then here, and then here. So you see, like maybe this ring is the fastest, and this ring is like quite slow. So okay, coming back to the problem which we are solving, like we want to find a better way to replicate our prepare, and we have several guiding principles for us. One guiding principle is that we don't want to do star we don't want the bandwidth between the primary and the backups to be completely unbalanced. The second thing is that we want to abide by the principle that we never ever send just a single message. Because if you send a single message and rely on that to get delivered, you will have to do a retry to fix that, and retries are horrible. Retries increase by modality. So, okay. Balance, no single point of failure. The third thing is that we want our algorithm to be dynamic and to actually take into account the current situation of the network, which at any given moment in time can change from a situation from an hour ago. So we want our algorithm to be adaptive to the change in the environment. And finally, we want our algorithm to have a cost function. We want to not only route around replicas which fail in a binary way, we actually want to discover the best route possible to use for our application. Okay, so how are we going to tackle all these challenges? And the answer is adaptive routing. That thing which I'm going to, well, given that we've passed half an episode, I think it will take us 2 episodes to cover this. But well, adaptive routing is what we will cover next. Okay, so let's maybe wipe the slate clean. Can I actually like do this? Okay, yeah, it works. Wipe a slate clean, reset zoom, and go back to our incredibly laggy experience. Which is completely unacceptable. Okay, so kind of like, hey, no, modern computers do not stop to amuse me. Okay, so what do we do to keep balance, to avoid sending a single message, to dynamically react to changes in the environment, and to find the best possible route? Well, there is several ingredients here. Let's for a moment think about finding, like, how do you find like the optimal route? Well, one thing you could do is that you could try to send ping bond messages like between any pair of replicas, and then you could like imagine like having like a certain connectivity matrix which says like, hey, you know, like here ping like 100 milliseconds, and here it's like 80 milliseconds, and here like 120 milliseconds. And then you look at this matrix and you run some kind of like graph algorithm to figure out what is the shortest. Actually, I mean, isn't this like traveling salesman problem? Well, it is traveling salesman. Like, you know, you want to find a Hamilton cycle, a cycle which visits every vertex, but which is the shortest. And I mean, given that like our graph is like 6 vertices, like it's no problem to actually solve that, like using like full like looking just at every possible route, or like, you know, using like this dynamic programming, which is like slightly faster for TSP. But anyway, it's kind of like you can do this. But the question is like, should we do this? And this is the thing, because the general pattern here is that we kind of like, there is like a thing we want to do. We want to replicate our prepare across the cluster. And to find out how to do this thing, we go and do a different thing. We send pings. And then we lure some information from these pings. And based on pings, we try to predict how the network will work for sending prepares. And it can work, but it could also fail badly. The fundamental disconnect here is that we don't actually try that thing we want to do. We don't actually try to replicate. We're kind of like trying to find a proxy measure, a substitute. But there is no guarantee that our proxy measure is sufficiently correlated with what we are actually interested in. To give a simple example, suppose that the property of our network is such that it is very fast for small messages. Like, well, let's say not every network, but just this link over here. So this link over here is like super fast for small messages, but it just doesn't pass large messages. Maybe there is some MTU misconfiguration somewhere on the route between those two nodes, such that every message which is like larger than 20 kilobytes gets dropped. So we get very tight ping numbers here because, you know, there's no large messages in this network. Pings are very fast. But when we try to send a larger message, prepare, we will actually fail. So that's kind of like one example. What might be wrong here. Here's another example. Suppose this replica over here has a very slow disk. Network is like perfect. It's like super fast at responding to pings, but like for some reason, like disk is like really slow. So when it receives the prepare, it takes like 1 second to fsync data durably to disk. So despite, and let's say like this is the primary. So despite our measuring of like network latency, like very low, like 30 milliseconds, our like prepare OK latency is 1030 milliseconds because of the slow disk. And there is no way we can detect this slow disk thing on this replica looking at the network. And this actually, but like ideally we want to know that disk here is slow, because if we know that this replica is slow, we aren't going to send like our messages to this replica. We'd rather to replicate to the other four replicas first, and leave this laggard to be the last replica in our replication topology, whatever our topology might be, just so that we get faster confirmations and we get faster commit from other replicas. So okay, this means that, like, you know, you really want to avoid building indirect models of a system, because you don't like you can't really trust your model. You can't really trust that your model models the system correctly, especially given that ideally we would want to handle unknown failures we cannot predict from the outset. There is another approach how we could still try to optimize this, and that is we can do trial and error. Like, you know, you could pick a certain replication root certain replication topology. And you run it, and you actually measure how good your this particular topology is. And then at some point later, you decide to switch to a different topology. You pick a different root. And you measure your actual replication latency across that route as well. Not only like the network thing, but the whole end-to-end thing, from receiving client request to receiving quorum of prepare case. And you compare those two latencies, and you realize, hey, actually, if I go the second route, it feels like on average I'm going to be 30% faster. And then you go and pick the second route, simply because it is just, in practice, faster. So that's kind of like the big idea. We'll also add to our mix of ideas here is that, and by the way, this idea comes from PCC paper, and PCC stands for concurrency control, pessimistic, predictive. Okay, PCC concurrency control. Okay, I'm not finding this paper. Let's see, link in our architecture. It should be there now. Okay, so this is the paper, and what PCC stands for. I always forget this. Sorry, I mean it's just completely irrelevant trivia, but performance-oriented congestion control. Okay, performance like doesn't really. I mean, like all congestion control is performance-oriented. But the brilliant insight in that paper is that we want to make our concurrency control outcome focused, results focused, rather than like building models and trying to predict what would happen if we do X. We just do X and then measure, and if it turns out that doing X is stupid, we stop doing X and we start doing Y. Okay, so let's again erase everything and try to do this again. Can we devise a good replication algorithm for TigerBeetle? Oh dear, what happened there? Okay, so let's make this Why am I always like trying to draw like a little crown for a primary? I don't want to do this anymore. So let's see that from this point on, like the primary will have like a nice nifty hat. So cool head, cool primary head. Okay, so this is the idea. We still will do kind of like a real replication scheme. But the difference will be is that we'll put the primary in the middle of the ring. So our actual topology will be something like this. So primary sends to this node, and this node forward to this node. And primary sends to this node forwards to this node forwards to that node. What is the property of this kind of like biased ring, rotated ring? Is that, well, primary sends to X. And that is kind of like a little bit skewed, but also not really, because if you think about this, So for a normal node, there is like one incoming, one outgoing message, while for the primary, it is like two outgoing messages. So it really like, it's not that like primary does twice as much work. It's rather when we place the primary at the start of the ring, the first node in the ring and the last node in the ring, well, like a chain. Last and first nodes in the chain actually have less work to do than everyone else. So in some sense, this one is actually more balanced when it comes to the primary. Okay. What else do we have from this basic like fork root? And that is like, you see, we have 6 replicas. And that means that with flexible quorums, our replication quorum is 3. But that means that like primary and its direct neighbors are enough for replication quorum. So that means that in the best case, we actually reduce the latency to replication because we don't wait for 2 round trips. We only wait for 1 round trip here and here, and we got our replication quorum. So that's actually good. So this is an improvement over ring, but not over a star. Although maybe actually it is an improvement over the star as well, because in the star you kind of like will try to send all those 5 messages simultaneously, and it might be slower than sending just 2 because they will be competing for the same bandwidth. Okay, that's good. What else do we have? Do we have fault tolerance? Okay, let me maybe draw this like more concretely with actual peer-to-peer links, because I mean we'll use this illustration afterwards. Okay, send here and send here. Okay, now it is not lion, it's like really I just can't draw at all. Well, maybe actually I'm even better at this one. There is a lag. Okay, so what about tail atlas tolerance? Well, okay, let's assume that this link bugged out. There's no this link. So neither this node, let's see, I draw a lambda, and neither this node nor that node actually knows about our prepare. Well, you see, we still have 3 nodes to the left of the primary. So yes, there will be like an extra round trip corresponding to the case where there were no errors, but still we'll be able to collect our quorum of prepare case without retries. Okay, that's fine. What if this node crashes? Well, again, the same. This link doesn't work, but the other link is actually enough for us to get enough replicas for the replication quorum. So you see, this is actually pretty nifty. If any single node except the primary fails, we can still do our normal replication without any retries. We don't have bimodality. Like the primary just like doesn't notice that someone is dead. The replica might be lost, but the cluster proceeds forward without any kind of noticeable slowdown. Okay, but still, kind of like, you know, still, if like, no, I don't want to send email right now. Okay, still, kind of, you know, if this link is dead, or maybe even worse, no, I don't want to do this. If this node is dead, we kind of like still want to notice that here actually now our latency is like twice as large. So we might want to periodically flip the roads. And this is that idea of adaptiveness is coming into the picture, because once in a while, we just go and try an alternative route. So, okay, I mean, I think I will use main picture here. Once in a while, we'll say, okay, what if I change my replication topology? What if I do this? Like 1, 2, and then I still send to this one, but this one sends here, and this one sends here. And you know, we do this like periodically, and we realize that here actually this is faster, and we are going to switch to it. So, okay, I think this basically describes this idea. And we conveniently are almost an hour, so let's call this a day. Okay, summary. So we discussed with pictures our replication protocol. And the basic idea, okay, so what were ingredients? Well, first of all, we looked at two replication schemes. The star scheme, which is super bad because it causes the imbalance on the primary, and the ring scheme, which is also super bad because it isn't fault tolerant. If you cut a single link in a ring, the whole ring unravels. So we figured out that we want to do something better. We realized that one guiding principle here is there should not be any retries in the algorithm, even in the presence of errors. So, like, you know, obviously, like, you don't want to have retries if things are going smoothly. But the trick is that even things are not going smoothly, even things are failing, you don't want to have retries. Or even, especially if things go bad, you don't want to have retries, because retries have propensity to exacerbate the failures. So you kind of like want retry-less protocols. Corollary here is that you never ever should be sending just a single message. Because if you send just a single message, then a single failure which kills that message will require you to do a retry. So you want to send at least 2 messages. And you also want your topology to adapt to dynamic changes in the network, to route around failures, but you also want not only to detect nodes which fail completely, but you also want to route around nodes which are just slow. Finally, to judge relative merits of different replication routes, you don't want to rely on indirect measurements. You don't want to measure pings and make inferences as to the time of replication. You actually want to measure the replication itself. And this gives the following logical algorithm. First, we use ring replication topology, but we place primary at the center of this ring, so that the primary has 2 neighbors on one side and 3 neighbors on another side. This ring topology still is balanced, but it actually delivers lower latency, and it is tolerant to a loss of every single message. If any message is lost, the ring still delivers you a replication quorum without any retries. Okay, then you want to make this thing adaptive. You want to make it dynamic. And the way to do this is that periodically you run a round of replication using a random different route and not that route which you normally use. And you measure time for your normal route and for that different route. And if it so happens that a different route is faster, well, you go and switch to it. Okay, and that's, I think, basically it. Next time, on Friday at 5 p.m. UTC, live on Twitch as usual, we are going to look at the actual code to implement this routing, and it's going to be like really nice exercise because this all is implemented in like a single file. There's like very little dependencies on everything else from our routing. But to keep you entertained until Friday, let me give you this puzzle. So as I've said, like one of the ingredients of the solution is that we periodically are going to run a randomized check. Periodically, we'll use like a random route to see if it is better than the route we currently use. But the trick with the random route is that everyone in the cluster should be aware that, hey, this is the random route we are going to use. Because if like the primary think that we are using random route, but everyone else hasn't got this message, and they use the old route, then the primary will incorrectly infer the properties of its replication scheme. So how we coordinate the replicas to make sure they use the same random route for the right experimental prepares. Okay, if you want to learn the answer to this question, then please join us live on Twitch at 5 p.m. UTC next Thursday, live on Twitch. And if you miss it, then no worries. This whole thing is going to be released on YouTube on TigerBeetle channel. Okay, folks, thank you and see you next week where we'll be more coding and less drawing.